In this illustration, we intend to calculate bearing capacity of a strip footing in the Abaqus software. In this picture, the soil has been displayed with yellow and infinite elements with blue colors. In this example, infinite elements have been utilized, so the waves will exit the soil and wouldn't return again. The purpose of this analysis is to obtain the bearing capacity of a strip footing using the Abaqus software and compare the results gained from the Abaqus software with those obtained using Terzaghi solution. In this example, Mohr-Coulomb and Drucker-Prager models have been utilized in order to define the properties of soil. In this picture, the bearing capacity obtained from Mohr-Coulomb and Drucker-Prager model and those gained from Terzaghi solutions have been compared together. I will enter the Abaqus software for simulation. I will click on Create Part. First, I intend to create geometric shape of the soil. I will select the modeling space as two-dimensional. From here, deformable and shell, enter the rough size of the tracing page equal to 100 and continue. I will draw a rectangle. Enter its height equal to 3.66 meters. Its length equal to 17.68 meters. And then click on Done. In the next step, I will click on Tools menu, then on Partition. Here, select Face and Sketch. Draw two vertical lines in this manner. Enter the distance between these 2 points equal to 8.84 meters. And between these 2 points equal to 1.52 meters. Then I'll click on Done. In the next step, I'll enter Property module and click on Create Material. First, I intend to define the properties of soil using Mohr-Coulomb model. I will click on Mechanical menu, select Elasticity and Elastic. Young modulus is equal to 207 megapascal. And Poisson ratio is equal to 0.3. Then I will click on Mechanical menu, select Plasticity and Mohr-Coulomb plastic. Friction angle is equal to 20 degrees. Dilation angle is equal to 17.83 degrees. Cohesion yield stress is equal to 0.0 0.69 megapascal and click on OK. Again, I'll click on Create Material. I intend to define soil using Drucker-Prager model. I will click on Mechanical menu, select Elasticity and Elastic. Young modulus is equal to 207 megapascal and Poisson ratio is equal to 0.3. Then I will click on Mechanical menu, select Plasticity and Drucker-Prager. Using this formula, you will be able to calculate the friction angle in Drucker-Prager model. Here, beta is the friction angle in Mohr-Coulomb model, that is equal to 20 degrees. In this manner, beta, that is the same friction angle in the Drucker-Prager model, is equal to 30.16 degrees. As described in the article, dilation angle is equal to friction angle. Therefore, dilation angle is equal to 30.16 degrees. I will enter flow stress ratio equal to 1. In the next step, I will click on sub option and select Drucker-Prager hardening. You can calculate material cohesion for plane strain soil. C prime is material cohesion for Mohr-Coulomb model, that is equal to 0.069 megapascal, and phi prime is friction angle in the Mohr-Coulomb model, that is equal to 20 degrees. If you place these parameters in this formula, you will be able to calculate material cohesion for the Drucker-Prager model. Here the quantity of D is equal to 0.1107 megapascal. You can calculate the Drucker-Prager hardening using this relation in which D is material cohesion in the Drucker-Prager model, that is equal to 0.1107 megapascal, and beta is the same friction angle in the Drucker-Prager model, that is equal to 30.16 degrees. If you put these parameters in this formula properly, you will be able to calculate the Drucker-Prager hardening. In the previous steps, the quantities of D and beta were calculated accordingly. Here, I will click on OK. In the next step, I'll click on Create Section. Solid, Homogeneous, Continue. Here select Mohr-Coulomb and OK. Again, I will click on Create Section. Continue. Here I'll select Drucker-Prager material. OK. Here I will make a copy of this material and name that far. Then I will click on Edit and remove its plastic properties. Actually, these properties are used for defining the infinite elements properties. I will click on Create Section, Solid, Homogeneous, and Continue. Here I will select Far Material, OK. I will click on Assign Section, select this part of the soil, Done. Assign the materials of Mohr-Coulomb to that, and OK. I will select this part, Done. Select Far Material, and OK. I will enter assembly module, click on create instance, OK, then click on translate instance, select the soil, done. First select this point and then this one and OK. I'll enter step module, click on create a step, select static general and continue. The analysis will be done in linear form. I will enter initial increment size equal to 0.025 seconds, enter maximum equal to 0.1 and OK. I will enter load module, click on create boundary condition, select displacement, rotation and continue. I will select this line, done, and close boundary condition of U1 for it. Actually, this line is the symmetry axis, and the model is symmetric to this line. Again, I will click on Create Boundary Condition, select Displacement, Rotation, and Continue. I will select the bottom of the model, done, and close the boundary conditions of U1 and U2 for it. Again, I will click on Create Boundary Condition, select Displacement, Rotation, and Continue. I will select this area, done, and close the boundary condition of U1 for it. I will click on Create Boundary Condition. Once again, select Displacement, Rotation, Continue. I will select this line, done, and enter the displacement equal to negative 0.127 meters. I will enter Mesh module, click on Seed Edge, select these two lines, done, consider one element for them, and OK. Then I will select these lines, done, click on Single, enter the number of elements equal to 6, enter bias ratio equal to 1.5, apply. I will select these lines, done, and consider 4 elements for them, and OK. Then I will click on Assign Element Type, select this part of soil, done, put the element family on plane strain. Here select quadratic and OK. Then I will click on Assign Mesh Control, select this part of the soil. Here select Structure and Quad and OK. Then I will click on Assign Mesh Control, select this part, done. Here select Sweep. Then I will click on Mesh Part and yes. Then I will click on Assign Element Type, select this part, done. Here put the element family on acoustic. Here select quadratic and OK. Here I will save the model. Enter the job module. Click on Create Job. Continue. OK. Click on Write Input. Right-click on this file and select Edit Notepad++. Rename this element to CINPE5R so that the elements will be changed into infinite elements. Here I will save the model, then click on File menu, Import and Model. Open the soil.inp file in this manner. As you observe here, these elements were changed into infinite elements, and as you observe, the finite elements have 4 sides and semi-infinite elements have 3 sides. I will enter job module, click on Create. Continue, OK, and click on Submit. The analysis was done successfully, so I'll click on Result. Here you observe deformation of the model. Here we intend to draw this diagram. The vertical axis is pressure and the horizontal axis is displacement. The unit of displacement is inch and the unit of pressure is pound per square inch. I will click on Create XY Data, ODB Field Output, and Continue. Here I will select this node and click on Save. I will click on Create XY Data, select ODB Field Output, and Continue. Here I will select Reaction Force directed at Y or the same RF2. Then I will select all these nodes and click on Save. In the next step, we should add all these reaction forces up together. To do so, I click on Create XY data, then Operate on XY data. Here I will select Sum operator, select all reaction forces, then click on Add to Expression and click on Save As. In the next step, I'll click on Create XY data, select Operate on XY data and Continue. Here I will select Combine, X-axis is displacement and Y-axis is reaction force. I will put a negative sign here and one here and click on Save As. In the next step, I'll transfer this diagram to the Excel software. The first column is displacement, the unit of which is meter. The second column is force, the unit of which is Newton. In the next step, we should convert the force into pressure. To do so, we only need to divide force by the cross-section. As you observe, force is applied to this area, so we'll only need to divide the force by this area of the surface that you observe in this picture. In the next step, we should convert the unit of displacement from meter to inch, then convert the unit of pressure from Pascal to pound per square inch, because the unit of displacement in the diagram you see in this article is inch and the unit of pressure is pound per square inch. So in this manner, this column is displacement, the unit of which is inch. As you observe here, the diagram having been drawn by blue color is related to Mohr-Coulomb. And as you observe, the results gained are concordant with those obtained in the article, and the final bearing capacity resulted from Mohr-Coulomb model is about 181 psi. In the next step, we intend to solve the question using Drucker-Prager model. To do so, we would only need to select Drucker-Prager material and click on OK. Here we should do all the same we did for Mohr-Coulomb once again for Drucker-Prager and draw all the diagrams which had been drawn in the last step again. Here the diagram drawn with blue color is the one obtained from in the Mohr-Coulomb model, and the diagram having been drawn with red color is the diagram obtained from Drucker-Prager model. Actually, you can compare the results gained from Mohr-Coulomb model with those obtained from Drucker-Prager. As it can be observed, the results in both models are quite the same and identical. The final bearing capacity using Mohr-Coulomb model 181 psi, and the final bearing capacity using Drucker-Prager model is equal to 181.6 psi. The final bearing capacity using Terzaghi model is equal to 175 psi, and as you observe, the results gained from Mohr-Coulomb model and those obtained from Drucker-Prager model are so close to those obtained from Terzaghi model, and there is a slight difference among Mohr-Coulomb and Drucker-Prager models with Terzaghi model.